This conference will now be recorded.
All right, good afternoon, everyone. Thank you for joining us today for our webcast on SLS 3D printing. Appreciate everybody's time today. I do want to keep this introduction brief and get right into the content. My name is Mike Story, one of the owners here at Beckatt Solutions. Matt Prey is also on the call today. He's my partner. Again, thank everybody for joining. Before we begin, I do want to remind everybody, please keep your computers on mute. We'll have a time at the end for Q&A. That said, if you do have a question during the demonstrations, we'll be keeping an eye on the chat, so feel free to leave your questions there. And also, if you want a full view, if you go look at the top, you've got a drop-down menu. You can change that from view everybody to view who's talking. And when we get into the demonstration, you're definitely going to want that on full screen. Again, our company is Beckatt Solutions. We're a Midwest-based U.S. reseller of 3D printing equipment. Besides the product line we'll talk today, we also sell FDM line in Ultimaker, a metal 3D printing solution in desktop metal, and an SLA DLP line in EnvisionTech. That said, in this webcast, we're excited to discuss SLS 3D printing, or selective laser sintering, which is an affordable way to produce 3D printed parts with good isotropic mechanical properties, making it an ideal solution for functional parts and prototypes. We're also going to showcase Sintratec, a Swiss manufacturer of SLS 3D printers who's relatively new to the US market. With that said, I want to introduce our partner on today's call, Alex Hussein with 3D Chimera, based in Miami. Welcome, Alex. Thank you for being here today. Alex is an engineer by education and has a wealth of knowledge in the additive manufacturing space. We are genuinely excited to partner with him and 3D Chimera to bring this exciting new SLS product line to the US market. I want to turn it over now to Alex and his team, who are going to give us a deep dive on SLS 3D printing and walk us through the Sintratec process, including live demonstrations of their platforms, as well as show us several SLS 3D printed parts. Alex, take it away.
Hey guys, how are you? Can everybody hear me okay?
Yeah, I can hear you just fine.
All right, perfect. So I'm going to go ahead and get set up on this side. What we're going to be doing today is I'm going to show you guys a little bit of a demo on how the Sintratec systems are going to work. So we're going to look at some parts actually getting set up in the print bed here. So this is the software, which is called Sintratec Central 2. I'm going to showcase that for you guys, and I'm also going to then take those files. We're going to throw them in a thumb drive. This one right here, actually. We're going to plug it right into the machine, and we're going to get a print started. Along the way, I'll show you guys some sample parts, as well as the Sintratec kit, which is kind of the baby brother to the Sintratec S2. So we're going to focus most of this on the industrial printing solution from Sintratec, but effectively everything that we talk about here will translate to the Sintratec kit, just on a smaller scale. So with that said, along the way, certainly if you guys have any questions, don't hesitate to put those into that chat field we were talking about. And if you just can't hold it in, blurt it out, and I'll be happy to address that. And we'll keep everything moving here smoothly. So with that said, I'm going to go ahead and get us started. I'm going to grab a couple files here that we commonly print. A lot of these are kind of like our typical demonstration parts. So if you are receiving any demo parts off of the Sintratec system from our team or from the team at Beckatt, these are likely some of the parts that you guys would see. So I just kind of drop these guys in here. They kind of auto place. I'm going to pull them off the platform one at a time. So this part right here is a strength part. We hang like a 150-pound heavy bag off of this all the time. We often challenge people to kind of pull that apart like a Chinese finger trap. Super strong, which is one of the benefits, of course, of the SLS 3D printing process. Because our parts are going to effectively be completely sintered, you have incredible strength, and nylon 12, which is the base material, has always been and continues to be a very strong material, commonly used in the industry and now used in the additive space. This is a detailed part here. So this is a nice part to show, different types of features. You might call that like a torture test for some other 3D printers. What's cool about the SLS technology is effectively everything that would be challenging to print on an FDM 3D printer becomes easy on an SLS printer. So support materials, not a concern. Overhangs are not a concern. Superfine details are not a concern. In fact, these are all strengths of the technology. Then we've got this guy here. This is sort of a fun part that we've been passing out to folks. This is like a little thing you can hang on your keychain to help reduce the spread of COVID. So pushing buttons or pulling doors open simple way to have something where you don't have to have your direct hands touching the doorknobs and whatnot. Then this is a kind of a really cool part. It's got some super fine details in it. We'll take a little bit closer look at that in a moment. And then this is one of our normal, like almost like a keychain that we print, and that's got Sintratec logo on there. So I'm going to show you guys how we would set up the build platform, how we might orient them, and a couple of the features of the tool. So the first thing we would do is going to orient this kind of on a top view. We're going to find a home for this part. So we'll just kind of drop it into place up there for the moment, and we'll keep going. I'm going to grab this part, our strength part. We'll take a look at this guy, and it looks like it might make sense to spin this guy around a little bit. So I'm going to go ahead and grab this, and we'll give it a little rotation there. What we want to do is get that kind of close. Yeah, looks about right. Get that down. Let me reset that for us here. So we can move it manually the way that we were just adjusting it, or we could actually go here and manually adjust that. So we'll kind of drop that in there. Now, whenever we're setting parts up in here, it's important to make sure that we're thinking about the build in 3 dimensions. So this is something that's a little bit different from the FDM technology, because we can actually control where our parts get built in 3D space. So there's no longer the constraint of having just a single part as it fits on the build platform. So of course we can drop it to the build platform. But what's really cool is that we can actually stack things in 3D. So for example, if we grab that guy, we can go ahead and we can duplicate this here, and we can start to build these parts in 3D space. So we can stack these right on top of each other, so that when they print, we don't have to worry about support material between them or anything of that nature. We can just simply get them where we want them, and we can get those printing. Now we'll see here we've got a little bit of an overlap on that guy, so we'll just sort of rotate this guy. Now, another cool thing about this technology is, while of course the coder is going to go in a particular direction, the parts are very, very similar strength in the X, Y, and Z, like regardless of orientation. So where maybe on an FDM technology, you're really thinking about the coordinate system or grid technology that's built into the machine. Here, we're going to get similar strength regardless of how we orient those parts. So we'll put this guy in here. Maybe we'll rotate this one. We'll find a good home for that in a moment. That looks like a good starting point. Now, this part I always like to talk about. This is our detailed part. Now, if this were in FDM 3D printing, we'd absolutely want to put the opposite side of this flat down on the build platform. This is like a big flat area here. Now, one of the cool things about SLS technology is that, one, the orientation of the part doesn't really matter. But two, when you do have a really fine detailed part here, actually the complete opposite of the logic you might have in FDM applies. So where the FDM technology might want to put that flat, here we're actually going to rotate that. So we're going to rotate that completely over so that detail is actually face down on the powder. And you can think of those details almost like little anchors, kind of holding the powder, the part into the powder in place. So I'll go ahead and orient this. So we'll look again from that top view. We want to make sure everything's fitting in there nicely. We can kind of just adjust that pack until everything looks just right. All right, that's looking okay. Now we've got this detailed part here. So this has got some really fine details. In fact, it's hard to even zoom in and see on this. There's actually a threaded piece here. There's some very fine parts. So we're going to grab this one. We're going to place this on the build platform. And again, we're going to want to rotate this so that the finest details are facing down. All right, so we'll go ahead and turn that 90. There we go. Now I'm going to look at that from the top view again, and we'll get this oriented in here so we're not interfering with anything. And we're almost done with our setup. Yeah, it's looking pretty good. All right, now we'll look at it from the side, make sure that everything is down at the platform where we're hoping to see it. So we can see in our process, we raised that guy up a little bit. So we'll just drop that down to the platform a little bit. We'll turn on, look from our different angles here. We can see this, this detailed part in the center is also kind of floating high. So we'll bring that down. Now we of course don't want it sticking out of the bottom of the platform, so we'll just kind of get that in there good. And it looks like this part right here, we could actually duplicate that and do another one stacked on top. We have the space for that, and that wouldn't really hurt anything for us. Might as well get the maximum efficiency out of the technology. That's really one of the cool things to think about with SLS as well, is that you can really maximize that three-dimensional space. So you're not only thinking about what can fit on the build platform, your volume is truly the three-dimensional build volume. So it can really open up a lot of room for like massive efficiency. So, you know, of course we could stack, we had smaller parts into these little in-between areas. But I think for now, this looks like a pretty good build. We've got a couple stacked parts. We've got some fine detail piece here. We've got our standard sample detail part here. And then we've got our keychain over there. So that looks like a nice build. So the next step here is we're going to run it through an analysis. This is going to slice up the part real quick. And it'll allow us to basically inspect it layer by layer, look at the details on there. So we're just going to take a look here, and we can actually see this is what our part's going to look like as it starts to sinter one layer at a time. So I'm just kind of working my way up there. You'll notice on the right-hand side, there's a little cylinder. That's a keep out area. That's where like there's an IR sensor that is measuring the temperature of the print bed. And this printer has a cylindrical build volume with like it basically has an infrared lamp up at the top. It's a full circle. So the temperature is completely even around the outside perimeter of the machine. And then this outside area here is a keep out area as well. So if we had something that just kind of stuck just a little hair in there, it'd be okay, but we're going to try and stay into the main print area for our best results. So that looks pretty awesome. That looks like a great setup. I think everything's going to turn out pretty well there. So we'll go ahead and do two things here. We're going to save our print job as well as our and export our part as well. So let me get in here, save our print job. All right, so we'll go out to our, let me see if I can find that on the desktop here. And let's call this print job, and we'll put today's date. What is that? The 18th. All right, and then we'll go ahead and save that out. That's going to be our STEC file. That's our basic file for the print setup on the machine. Then we'll also go ahead and generate our print file, which is going to be called our PEX file. So our PEX file is basically the G code that we might have had if we were printing on the FDM 3D printer. It's just a format that the Sintratec reads. So we'll go with a similar name, print job, and we'll call it 08-18. All right, we'll save that guy out. So it's going to run through that slice one more time. And it's literally doing the same thing we looked at on that analysis. And it's going to create the instructions here for the laser system to operate. So what's really cool on the kits as well is that we're utilizing a Galvo-based laser system. So that's true on both the Sintratec kits as well as the S2, which allows them to print super fast. So we're looking at print speeds usually somewhere between 4 and 6 times the speeds of any competitive technologies that are out there. So while it's a small system, it packs a big punch, and it can lead for really major efficiency when you think about the speed on the laser path, as well as really packing that three-dimensional space there. We find that most of our customers who are working with Sintratec are pretty commonly using FDM technology today and maybe outsourcing parts. And so there's really a lot to learn as you're thinking about this new tech. And I really encourage you guys to ask questions as we go. I'll be happy to kind of go into the weeds on any particular topic. All right, so that's that. We're ready to print. So I'm going to save that out. This looks like the folder I was working in there. Yeah, that looks good. So I'm going to find my handy dandy thumb drive here. We'll plug it in.
Hey, Alex?
Yeah.
Hey, it looks like we got some questions over in the chat bar. Can you see those?
I can't see them as I'm doing this, but if you want to read them out to me, I'd be happy to address them.
All right, so one of the first is, how does SLS 3D printing work, and what are some of the advantages?
Okay, yeah. So the SLS technology is basically going to be a powder, like a nylon 12 powder. Now you can use other powders on the Sintratec printers, particularly the Sintratec kit is really good for different powders. In general, the way it works though is we're going to lay down a layer of powder, then we're going to preheat that powder right before its melt temperature. and we're going to hit that with a laser right at that point where we want it to sinter. And that's going to turn the powder from a gray color to like a melted black color. And similar to FDM 3D printing, we're going to build it one layer at a time. So we basically melt that layer, we wipe powder over the top, and then we sinter another layer right on the top of that. So some of the advantages of that technology are that because we're working with a powder and we're not worrying about a nozzle diameter, we can get really, really fine details on parts, which is something that can be challenging in the FDM process. In addition, what we can do is, because our parts are built basically in a cake of powder, because we're building the powder over one layer at a time, you actually have effectively built-in support material everywhere that you are building your part. And so you don't have to worry about the orientation of the part or how you're going to dissolve out the supports or break out the supports. All that is going to basically just be as part of the process. So it can really lead to a lot of advantages in design freedom. So a lot of the promises that we've heard of and seen in 3D printing over the years with maybe generative design or parts that have lattice-based structures, integrated three-dimensional textures, all of that suddenly becomes possible in SLS 3D printing, whereas in the FDM process, you really got to go through a major design for additive approach in order to optimize your geometries to work with the tech. With SLS, it's almost like you have like ultimate design freedom. You don't have to worry about draft angles and things like you might in injection molding. You don't have to worry about tool paths like you might in CNC. You don't have to worry about overhangs and undercuts and support material like you might in the FDM process. You can literally just design your part, hit print, and it's going to come out great every time. All right, that help a little bit on that
that's
question
great.
there?
Thank you. So Anna says,
okay.
Yeah, I think so. I'm sure there's going to be more questions. We've got a few more, but why don't we continue on and we'll address those at the end if that's okay with everybody.
Yeah, totally. We're going to have a break here in just a moment. I thought I'd come over and show you guys the machine a little bit. So I think what I'll do is I'll figure out how to stop sharing my screen. So that'll open up the view a little bit. And this might be where you want to focus on that one camera so you can kind of see a little bit more in the background. This is the Sintratec S2 system. This is Julian over there. Say hi to Julian. So basically, we have two major components here. We've got this guy right here. This is our laser system. So in there is actually the laser for the printer. We're going to be putting our material handling cart in there, and it's going to be actually where all the sintering happens inside the system. Then we have a second station over here. This is our cleanup station. It's also our preparation station. So this is where we're going to basically load the powder and get everything set up. So that's the first place that we're going to go here in order to get your print set up. So here's our thumb drive. I'm going to hand that over to Julian. And what he's going to do is basically load it into the printer here. So we just got a little USB there. And on the display here, see if I can get that in a way you guys can see it. He's going to actually go through effectively like a wizard in order to load the powder. So he's going to go in here, select the print job, select the material, and you might have heard the system start to power on there. So basically at this point, what's going to end up happening is these platforms are going to adjust to the correct height, and he's going to be scooping some powder into the machine. So I'll leave him there in the background. We can kind of see him doing his work. This might take, I don't know, like 5 minutes or so for him to get the powder loaded. So this would be a great time to address any of those other questions that might have come up.
Okay, so Anna says, so cool that orientation no longer matters, but is that really true? Does orientation not affect print time with SLS 3D printing?
Good, great question. So the main thing that affects print time is going to be your height in the Z direction. So for sure, if you have more layers, it's going to take more time to print, right? But what's cool about that is it's not the weakness in the Z direction that you might have typically seen in the FDM process becomes really something that's not a major thing to consider. And so like the strength part I was showing you, for example, we laid it flat today, and that's great for efficiency in terms of print time because we're reducing our print height. We're able to pack it really dense. But we sometimes have print jobs where we've got just a little sliver of space, and we actually orient that standing up, and we're getting very similar strengths on that strength part when it's pulled, even though the cross section basically has like a single layer at that area where it would have to break. Because the layers are completely bonding as they sinter with that laser, you're getting a really, really strong part.
Big bug door. There's a big bug.
Great. Well, thank you, Alex. There's another question that came up. Does Julian need to wear gloves? And so I just want to ask about kind of the PPE when dealing with that system in general.
Yeah, great question. So yeah, you do want to wear gloves. I mean, you are working with powders, and so it's not so much like that we're worried about it like absorbing into your skin. It's just like touching any type of a plastic. But what you're actually trying to do is prevent any little oils from your fingers like getting into that powder. And so we do wear gloves for that. Of course, like nobody wants to have like grimy powder under their fingernails either. Now, when you are working with the powder and you're kind of moving it around, whether you're mixing powders or loading them, you do want to wear a face mask. So here in COVID times, we've got face masks on pretty much all the time. So that's what Julian's got going on here. But under normal circumstances, you still would want to wear a mask. You don't want to be like inhaling the powders, right? It's not like carcinogenic or anything. It's a non-toxic powder. But with that said, inhaling any like super small particulate's not great. So in general, those are the two PPE things that you're going to be thinking about. You're going to be wearing some gloves, and you're going to be having a mask on as you're moving the powder around. Beyond that, it's a pretty straightforward process. In fact, for those of you that are familiar with FDM and breaking away supports, we're using like sharp tools and massive amounts of force. We don't have any of those risks here. So we're not chopping away at stuff trying to break things away. We're not working with caustic chemicals to dissolve out supports. We're literally just basically putting the powder in, and the heat of the chamber as well as the power of the lasers doing all the work there. Are you all done with the power loading? All right, cool. So I'll show you guys what the loaded powder looks like here. So once it's loaded, that platform, you might remember it had kind of like a cylinder and rectangles before. There's basically like one here and one here, as well as one in the center. Those are the three platforms. So basically there's going to be a coater that goes across from one side to the other and wipes the powder. This is the coater right there in the corner. And basically that's how it works. So at this point, I'm going to step back. Julian's going to go ahead and move the cart there from the cleanup area where we loaded the powder, and he's going to move it over into the sintering station. So we drop that down, and now we're connected. So he's going to literally grab that same USB drive with that same exact file. So it had the instructions for both loading the powder, knew exactly how much powder you needed. And now he's basically going through that, and he's going to select that print job in order to get started. That's it. So now we're printing. So basically what's going to happen now is the printer is going to go through a preheat cycle. It's going to heat the powder, heat that chamber up. That cylinder basically has some like heater pads wrapped around it, which allows it to heat up pretty quickly. So I'm not sure exactly on the timing, but if you stick around for the full time, there's a very good chance right at the end of the call, we'll have finished through our preheat cycle and we'll start going through our first couple layers. That's always the most exciting thing to see. If you guys can't see that, we'll be sure to share some videos so that you'll be able to see the part printing and understand what the cleanup process would look like a little bit as well. But yeah, that helps. These have been some fantastic questions so far. Maybe we can answer a few more questions as we go.
Do you want to continue now, or do you want to jump into a few more questions, Alex?
Let's do one more question, and then I'll show you guys the Sintratec kit.
Okay. So why is it called slicing when a laser is supposed to be curing the plastic powder? Cool.
Good question. So we're basically taking the 3D file, and similar to FDM 3D printing, we are slicing it into layers. So we're literally slicing that 3D file into different layers. Those layers are going to basically be 0.1 millimeters thick. And then each of those layers is going to basically cure or melt that powder. So any software that we use to prepare a 3D file for 3D printing, we call that slicing because we're breaking it down into layers. A good way to think of it is like, think of a loaf of bread. We're going to slice that loaf of bread into layers, and we're going to make each layer. Now, it's a little different than making bread, but it's sort of the same idea. So let me show you guys the Sintratec kit here. So these are the Sintratec kits. We've got some twins here on the kit. So basically, it's the exact same type of system. It's just on a smaller scale. So I'll go ahead and open this guy up. I think we actually finished a print earlier today in here. So yeah, there's going to be some powder in there, but you can kind of take a look inside. So we basically have two chambers as well, a left side and a right side. And then we have this coater, which comes across and wipes the powder. The laser's up in this area here. And then the whole chamber is basically like a little oven. So this guy basically gets hot. And then the laser is able to cure each layer one at a time. So to help you understand the size difference a little bit better, I've got a reference here for the size of the Sintratec kit. So it's not too shabby. It's like around like 4 by 4 by 4 inches, something like that. But if we compare that to the S2 over here, show you some examples, you can see the size of that cylinder there, right? So the S2 is about a 6-inch diameter by about 15 inches tall. So it's a huge difference in terms of the build size on the parts. But what's really cool is the finish on the parts, the surface details, all that's going to be identical. So, you know, I happen to know which parts were printed in which technology here on our like little demo table. But in general, they would be indecipherable. So like, for example, here's a part that was printed off of the S2. Okay, looks beautiful. Nice detail. Let me show you another part. This was printed off the Sintratec kit. Fine threads, fine details, holds pressure. So you can see the finish on the parts is pretty much indecipherable between the two technologies.
Actually, that leads, there's another question kind of along those lines of that part you just showed, Alex. Norm
Sure.
asks, if you were to print a vessel, would it be capable of holding low pressure, 20 PSI or less, or would it leak like an FDM part?
Yeah, great question. It's not going to leak. So in the SLS process, the parts are going to be fully sintered underneath that powder layer. So let me see if I've got an example. You know what I'm looking for, Julian? All right, cool. Well, that has one that has a cross section through it. So in general, when we're looking at this technology, you've got the powder on the outside, right, which is going to kind of be like a gray color. And on the inside of the part, it's going to be fully sintered, going to kind of look leathery. So you see that detail there? That's the inside of a part, the cross section on a part. So on the outside, you see kind of the remnants of the powder, and on the inside, it's fully solid. And unlike FDM 3D printing, everything that you print is going to have a solid cross section in it, unless of course you design it so that it has an open area in the middle. That's a big difference. So in the FDM 3D printing process, we are not working on doing anything with like infill densities or anything like that. All of it's going to be in the 3D file itself. So the slicing parameters are way more straightforward. As you saw, it's basically like put it in and slice it. So we're not messing with different types of temperatures or different types of infill densities, layer thicknesses, perimeters, etc. Unless you really want to. Of course, you can dig in deep, and the Sintratec kit's pretty good for that if you're doing experimental stuff. We work with a lot of like government labs, like national labs, as well as like research institutions who love to like dig in and get into those details. But for the most part, when you're working with the printers, they can be like kind of a simple plug and play.
Great.
All right.
Thanks, Alex.
I'll leave the camera here, but go ahead and what's the next question you guys have there?
Sam asks, what are the tolerances of the parts printed, plus or minus?
Good question. Yeah. So tolerances. Let's see. I'm going to actually grab Julian here. Julian, when we're printing something on the SLS technology, what would you say is kind of a typical tolerance for the tech?
I'd say probably plus or minus a quarter millimeter.
Okay, so I'm not sure if you guys heard that. He basically said, in general, we're looking at like plus or minus a quarter millimeter or so.
Okay, great. I think I missed one.
Okay.
Yeah, I think I missed a question from earlier. Ned asks, I noticed the build chamber is circular. What's the advantage of that?
Oh, yeah. So the cylindrical build volume allows us to quickly heat up the build environment. So under a normal 3D printer, we're mainly using like heaters around the outside in a square. And you can imagine as you're kind of wrapping something around a square, the corners end up being the most difficult areas to heat. In fact, Sintratec did a bunch of research and discovered that the corners took the vast majority of the time to preheat the build volume. And so by cutting the corners off and working with a cylinder, they were able to more efficiently heat the build volume without worrying about those cool corners. And also, they were able to reduce the cost of the system by simplifying the number of heaters that they needed to use. And so the Sintratec S2 is the only SLS 3D printer on the market that utilizes a cylindrical build volume, and it's pretty unique for that particular characteristic. You could even buy a $1 million SLS 3D printer and you won't find this feature.
That's great. I think we're caught up on questions, but maybe you want to show us a few more parts, Alex, some from the kit and some from the S2?
Yeah, totally. Let me show you a couple more details here. So this is always a really cool part. So the Sintratec printers can print different materials. So on the S2, we're mainly looking at PA12 nylon and TPE. On the kit, those are going to be our default materials as well, but it is an open material platform, so we have a lot of people doing research on that. Sintratec has also released recently some information about some new materials, so we'll be seeing glass bead reinforced nylon as well as a carbon fiber reinforced nylon soon. But this is really cool. This part right here is a TPE part. So, lots of details there, but this is actually a rubber part. So, imagine what you can start to do when you have the design freedom to make intricate details like this that are also flexible like rubber. I'm going to show you another example here. So this is another part, one of our most detailed prints to date. You can see super thin wires on there. Those are like, I think, a 0.5 millimeter in size. And again, totally flexible. So that's pretty cool. Those particular parts happen to be printed on the Sintratec kit. And you can see that we actually get very similar detail. So here's a PA12 part. This is that detail part we're printing right now. So you might be able to see some of the threads on that in the center area, some of those fine details. Now this one's nylon, PA12. Here's the exact same part in TPE. Same level of detail, except squishy. So if you're in need of making flexible parts that have super fine details, this can really be an incredible technology to look at. Now we have people who are looking at like revolutionizing their industry. So, the orthotics industry is an industry that's like ripe for innovation. If you're familiar with how orthotics are made, it's a super labor intensive process where they're doing vacuum forming, tons of labor in order to produce a part that is starting to become commoditized. And so what the more innovative companies in the space are doing are actually taking 3D scan data of the foot and actually manipulating that and making a 3D printed orthotic that can be put in a shoe. Now these little guys are a pretty big game changer. In addition to being able to make the thin wall features here and adjust the thickness of the part, you can suddenly do things you could never do before. So for example, in an old school way, all this part had to be a consistent thickness because we're doing a vac form. Now we could have a thin area in the front where we want it to be flexible. We could have a thicker area in the center where you have a weak arch. And we could have a thinner area back on the edge here where your heel mates up with the shoe. So you can start to do things that were previously impossible to do in your industry just by taking advantage of what this technology can allow you to do. This is another really cool part. This is for a medical device manufacturer that we work with. There's some crazy thin like machine threads there. They actually used this system as part of like a test rig to do a fine adjust on like a laser optic system. And so they needed like really fine details, and their turnaround time from their machine shop was something like 6 weeks to get that level of precision. We're able to print this for them overnight on our machines because there's really nothing we have to do to make a precise part or prototype. It all prints at the same level of precision every time.
Alex, those parts, they look great. And I could see how the precision, the level of detail, and the versatility of the materials can lend itself to a lot of different applications. But how would these parts compare to, say, FDM 3D printed parts in terms of both functionality and appearance? And also, some people might know the HP line of multi-jet fusion 3D printing. How do the Sintratec parts or other SLS compare to the HP 3D printing process?
Yeah, great question. So, in general, let's start with FDM as compared to the SLS process. So, when you're thinking about the FDM process, there's a lot of great advantages to that technology, right? We can go with a really large variety of materials. The costs on those materials are quite low. And, finally, we're at a point in the industry where we're starting to have some of the big players in the plastics world starting to introduce high quality materials that work on a variety of machines. So you're going to have a great advantage there in utilizing those systems for all sorts of applications. So don't get me wrong, I'm not knocking it. Like, here's an FDM 3D printer right here. We do all sorts of FDM 3D printing. We absolutely love it. But there's always going to be a trade-off with that technology when you're thinking about getting into fine details, when you're looking at doing short run production, when you're looking to do some type of volume 3D printing, when you need to have that extreme level precision, and when you're thinking about how we're going to do, complex geometries. Like, look at this guy, for example. This is a lattice structure that was built utilizing a gyroid type of geometry. It's theoretically possible that you could print something like this on an FDM 3D printer if you had dissolvable support. But I'm yet to meet anyone who has any FDM 3D printer that would have the capability of doing that while also being a completely flexible material, right? And the reality is, when you're looking at an SLS technology, the options of what can be done expand greatly. So, this is an FDM part with dissolvable support. It looks pretty good. I mean, it's pretty awesome. We can create, this white stuff is going to dissolve out. Do we happen to have the dissolved version of this guy somewhere? I think we do. And it'll turn out like this, and that's great, right? But if we were to print that exact same part in the SLS process, let's look at this guy, for example. Can you open that so I don't drop it? So this part we printed on a Sintratec kit with no concern whatsoever for dissolvable support. And not only is this an intricate geometry, these pyramids actually, it's hard to see in the video, but they're completely loose. They're not connected in any way. They're just like interlocked from the geometry. So something like this printing in the FDM process will be tricky. Now, would you need to print this in an engineering application? I don't know. Maybe there's some interesting new technology that you can develop by having features that are able to move within each other. And so, when you start to look at the SLS technology, you really start to open up the options of what you can do and what constrains you in the process. One of the things that I like about it is that if you're designing parts for injection molding, for example, your geometries are effectively optimized already for SLS 3D printing. Because one of our strengths here is going to be the ability to print thin wall features, the ability to print really fine details. So even if you've got all your drafts and rounds inside of your part, even if there are snap fit features, all that's very likely to work perfect right on their first print on an SLS printer.
That's a great answer. Thanks, Alex. But along those same lines, many of the folks on this call are probably very familiar with FDM. How does the learning curve of SLS compare to FDM as terms of ease of use of a 3D printer, for example?
Yeah. So the learning curve in the SLS process is going to be, I think, actually a lot easier than the FDM process. So just like FDM, there are certainly design rules that you want to consider when you're developing something for additive using this technology if you want to get the most out of it. But unlike the FDM process, you don't really have to be like an expert at slicing and an expert at like fine tuning your machine. The FDM world, there's still a lot of like literal knob turning and like turning wrenches in order to like adjust things and level them and double check and triple check that the gap between the nozzle of the plate is perfect, or that your adhesive between the plate and your material is great, and that you got the right print temperatures and you're going at the right speeds. And it could be a little overwhelming for people who are first starting with the process. With the SLS technology, I mean, you literally saw what it takes to take a part today. In fact, we took like 5 or 6 different parts, drop them into the slicer and hit print. So I think for most folks who get started, we find that our normal training session is like a 2-hour session, a remote session, and that's more than enough time to get everybody up and running. Some of our more advanced customers are really trying to like squeeze every ounce of value out of their technology, opt for like a full day of training. And within that, we have a very short period of time focusing on the technology itself and how to operate it. And the vast majority of the time is digging in deep on their specific applications and looking at how their designs could be optimized to completely take advantage of the process.
Awesome. How are we coming along with the S2 over there? Do we have time for a couple more questions, or is that ready to go?
Sure. I'll let me move my stuff here. I'll have Julian check and see where we are in that preheat cycle.
Okay. In the meantime, Anna wants to know, what are the print time for some of these objects?
Yeah, good question. So about 12 minutes to, okay. Yeah, we've got maybe another 15, 20 minutes or so on the preheat cycle here. So it's going to be right on that bleeding edge to get the print started. So regarding the print time, this printer is going to print at exactly 2.4 centimeters of height per hour. So it's kind of a strange way to think about the 3D printing process. So let's say this is our build volume, okay? And that's our keep out area there. So if I put one part in, let's say this guy, which, let's say that's 1 centimeter tall. If I put that in the print volume like that one part is going to take me roughly a half hour to print. Now, if I put a second part in, it still takes me exactly the same amount of time because the laser moving around is so fast, that's not the main driver of the time. The main driver is putting the layers of powder over. So this is still a half hour to print. Now, if I took this part, this guy, this random part, put it in here, still a half hour. If I add this guy, still a half hour. If I add this part too, still a half hour. If I took this part and I lay it down, still a half hour. But if I suddenly put this part standing up where it's twice as tall, now we're at about that 2.4 centimeters. And this guy is going to take a full hour to print, just this one extra part, right? So that's why it makes sense to take like something like this and stack a few of them up to efficiently use that space. So the time is based on the Z height. That's the main difference. So in FDM, if this took an hour to print, you add a second one, it takes an hour. You add a third one, it takes another hour. You add a fourth one, it takes another hour. You add a fifth one, you're looking at 5 hours. But in the SLS process, if we put 5 of these in here, that still takes the exact same amount of time. So there's a fundamental difference in the way that time is calculated in the SLS process versus in the FDM process.
Well, and with orientation not being a concern, since the powder is self-supporting, you really can maximize your time by really batching the builds and just maximizing the build volume space.
Absolutely, yeah. I mean, for those of you who are used to like outsourcing parts, you may have noticed, like I think a few years ago, some of the lowest cost lowest cost outsourced 3D printing producers all adopted SLS technology from the very beginning. And the reason they did, and they're using way bigger machines than this. They're like using $1 million machines back then. And they're still today almost $1 million for those types of huge machines. But what they did is you would order a part and it might take like 6 to 8 weeks to get something back because what they were doing was filling up that entire build volume. And they're filling up the entire chamber and they're using it to its absolute maximum efficiency. So what Sintratec looked at something like that and said, can we bring this to a regular engineering shop, a regular design shop, a regular product development company where they're not, taking in orders from everywhere. Maybe you are going to have small batch orders that you need to run through the system. And, you can take advantage, get all of those, benefits that you have of working with a service bureau, but you can do that in-house and you don't have to pay for their overhead, right? So those guys, that's how they're making their money, is they're maximizing that efficiency. At the end of the day, the raw material cost is a fraction of the cost of the actual print. Most of the cost that you're going to see from a service bureau or anybody who outsources, they're recovering for their time and marking that up. So by having a system in-house, you can bypass all that and actually have a system that gives you the same types of quality at a fraction of the price. So, you know, you think you had mentioned like, how does this compare to like HP technology? You know, we don't like to like get into head-to-heads and trash talk any technologies. I mean, it's a great printer. They're expensive, the HP technology. We have a lot of customers who have them and also have Sintratec printers. We have a lot of customers who are considering them and decide to buy Sintratec printers. Usually what they're looking at is an ROI and doing that cost benefit. And what you see is that on a Sintratec, of course, with it being a fraction of the price of something like an HP system, you're going to get like equivalent performance, you're going to get equivalent surface finish, equivalent details at a fraction of the price. Now that comes with a trade-off of size. You know, the HP systems are really much bigger. So if size is the key criteria, then maybe that's the way to go. But, you know, we can print something like this on a Sintratec S2 without any problem. This is actually a really cool part. If you remember, like back in the day, like there's, you know, kind of like swords that expand out. This is actually all printed as a single piece on the printer. So self-expanding, and I know it's hard to see. This like chainmail on the outside is actually loose, and that's all printed as part of the process as well.
Wow, that is a super cool part.
Yeah.
You're going to send us one of those, right, Alex?
Yeah, right.
So we do have a couple questions that go hand in hand. How much
Sure.
of the printing stock or powder is wasted during a print? Say if you must print like a long thin part, for example. And then similarly, how do you control the powder after each print? Can it be recycled? Will it require a new batch of powder every time? How do we maximize the powder when working in the R&D world?
Yeah. Such good questions. Like some of my favorite ones. So, in general, the Sintratec systems are beautiful because the powder is like 99% reusable. So all of the powder from your print, you can reuse that's left over. So that's going to be the powder that was built around your parts that we would consider like support material in the FDM world. You're not going to grab that and throw it away. You're literally going to vacuum that powder up in the system, and you are going to find a way to store that into a storage container. So we've got a system that comes basically with the S2. Let me see if I can get it over my shoulder there. You see those drums back there? There's like a kind of a vacuum system. That's all part of the system. And basically what you do is you select the right drum. So there's 3 drums. There's basically one for virgin powder. There's one for completely used powder. And then there's one for print ready powder. And so what you do is when you're done with your print, you're going to vacuum the powder up, whether it's the waste powder in the bin, whether it's like the overflow from the print bed that's coming across when you wipe, or the the breakaway support material, if you will, that you vacuum up. You're going to suck all that into that used drum. It goes through this cyclonic separator, which actually does a really good job of breaking down any clumps back into like its constituent parts of raw powder, and that's going to stay in a bin for the used powder. When you're ready to mix powder, the system has a semi-automated process here where you basically you're going to put that cart into the system, and you're going to basically tell it how much powder you want to have mixed, and it's going to lower the platforms, and it's going to tell you like platform 1, it's going to lower to a certain height, and it says go ahead and put used powder in here. And then the platform on the left, it's going to lower to a certain height and say I want you to put virgin powder in here. And it's going to set up the exact ratio for you with the exact volume that you set up. And then what's going to happen is a wiper is going to go across the top, and we have this little vibrating platform that you put over the build area, and it's going to actually sieve the powder for you. So it's going to wipe across, it's going to vibrate, and any like leftover like clumps that are still there in the powder after the vibration, you toss that. Usually for like a full cylinder on the S2, we're looking at like maybe a bottle cap or 2 of like debris that's left after that sieving process. So you're really looking at like maximum efficiency on the machine. The way we like to think about the cost of a part is we literally look at the volume of the part, like geometrically, and we just have a simple factor. We basically take the cost of the powder divided by the volume of the powder, and we multiply that by the volume of the part, and then you have your actual cost per part. So it's a really simple like linear relationship, very little waste to consider.
So along those lines, Alex, we talked about how 3D printing or SLS 3D printing is an affordable way to produce great prototypes, functional parts. Can you show a few examples, just a couple different parts, and maybe estimate the costs of the materials?
Oh, sure. Well, I wouldn't have the cost right off the top of my head, but what I can help you to understand is how we do that. So basically, if we look at something like this, what we're going to be looking at is its volume in like cubic centimeters. So the cost per cubic centimeter, I believe it's around like 7 cents or something like that. So that's basically how you do the math. So you're effectively going to look at that cost per cubic centimeter and multiply that on through the part. So, you know, something like this guy or something like this guy, certainly it's less than $1. Maybe it's like, you know, I don't know. It'd be hard to venture to get, I guess, without looking at the numbers. So if you've got an application that you'd like to get some cost estimates on, because it's basically simple math, you can just send those over and we'll be happy to give you a quote, not a quote, but an estimate of what the raw material cost would be.
Yeah, that'd be great. Just a couple more questions, Alex. With SLS printing, would it be reasonable to print a reusable part with the spring included in the print design? Say the spring force controlled by the thickness of the spring in the print. That's from Kyle.
Yeah, that's a good question. For sure, I'm just looking around here to see if we happen to have anything that has a built-in spring. But most definitely, the answer is most definitely you can do that. It's a great use of the technology to be able to integrate something like that. And absolutely, yeah, you can adjust the resistance on the spring by all the same parameters you'd use if you were designing a spring out of metal, right? So the cross-sectional diameter, the thickness. Of course, you could do crazy stuff like you could vary the thickness across the part. You could give it varying coils that change over height, things that would have been impossible to do, you know, with a traditional spring. You could definitely do. So yeah, that would definitely work. That'd be a cool application for it.
And then Greg wants to know how hydroscopic is the materials, especially the materials such as nylon?
Yeah. So in general, nylon, as you alluded to, loves to soak up moisture. So that's just kind of a default characteristics of the material. Now, what's pretty cool about the technology is we're not so much worried about that when we're working with the powders, because we're effectively like preheating it in like a little oven furnace thing. So we're going to burn out any moisture that's in there during the preheat cycle. That's actually part of what we're doing as we're preheating the powder. So we're not really worried about too much moisture in the powder. We do store them in like an airtight bin. So it is important. You don't want it just like out to the open air, no matter where you are. So you might have heard in the beginning, our office is based in Miami, Florida. So, you know, we are like humidity capital of the world. So, you know, we've got AC running 24/7 to help keep the humidity down generally in our office. That's actually more for our FDM 3D printers than it is for our SLS machines. So like on our FDM 3D printers, we've actually had to develop our own dry box systems back in the day before you could buy dry boxes. And that was critical even with our normal climate control. You don't have any of that stuff to be worried about in the SLS process. Now, if you were putting an SLS part like underwater or something like that, it is going to absorb some moisture and change a little bit in terms of its geometry. So there's some things that we can do to overcome that tendency. What's neat about the technology is that this powder on the outside almost acts like almost like a sponge, if you will, like on the outside. And so you can put penetrants on this material and it can soak those up, and then it helps to seal it up. So one of the things that you can do is you can dye the parts. So the best color to dye them is black. So I know it's kind of hard to see with the lighting here. Here's a black part. Let me see if I can compare like a gray part. You can kind of see the difference in color there. So you can definitely color the part, and you can get, you know, a dark color dye in there. That actually helps to seal up the part a little bit. But part of the way that that color gets in is because nylon absorbs water, and we're using basically like a RIT dye in water, and it's going to soak that up. Now, once that is kind of soaked that up and that colorant is in the surface, you're actually starting to seal up the surface a little bit. We also have some chemical treatments that you can do that will penetrate into the surface, and actually it's like a polymer dissolved in a solvent, and that will wick its way in through capillary action into any little tiny gaps. It'll close those up and actually make your part watertight. So we have a lot of customers that need to make watertight parts, and that's the technique that they use. They're going to use that penetrant in order to seal them up.
That's great. Thanks, Alex. I know we're getting close to the end here, so I do want to be judicious of the time. But a couple more quick questions. Are there any additional materials coming out for Sintratec in the near future outside of TPE or nylon?
Yeah, absolutely. So yeah, TPE and nylon are going to be your defaults, and then we're looking at a glass bead reinforced nylon, a carbon fiber reinforced nylon, as well as a polypropylene. So polypropylene has been one of the ones where we've been seeing really like huge amounts of interest, and that's going to be a great material as well. It's super durable. We've got a couple of videos of that on YouTube. It was announced last year at Form Next, so if you were to like search on YouTube for like, I think like new materials Sintratec Form Next, you'll see my beautiful face there, and you'll see some of the examples of the new materials that are coming out.
That's great. How porous are the parts? Are they gas tight? Can nitrogen pass through?
Yeah. So the parts are going to be pretty gas tight, and the porosity is really on the outer surface of the part rather than like through the part. As you saw on that one sample part, the parts are effectively fully dense on the inside. So it's not the same as like FDM 3D printing where we're putting stacking a layer on top of a layer, right? Because this layer was once molten and then is cool, and then we put another layer on top that's molten, and they sort of stick together, but we end with these micro cracks in between the layers, and that's what makes an FDM part porous. In the SLS process, we're not doing that. So this, for example, is like one of the very first parts I ever printed. This is actually my wedding ring. So we're going on about like 3 years here on this guy, and you can see it's completely solid. Have it on my hand every day. It's a nice, strong material. And this was just hand polished, right? So you can see inside, there's really no concern about it, like absorbing, shrinking, changing sizes from moisture or whatnot. Now we haven't run nitrogen specifically through. Sounds like a good application for a test. So if you've got an application like that, perhaps it's a good time to commission a part and kind of try it out.
Great. Awesome. Are we close there on the S2, or do we have a little more time left?
Let me see. How long are we on the preheat there? Looks like we're going to have about 10 more minutes, so I think we've hit the end of our time here. What we'll do is we'll capture a video of that for you guys, and we'll share that with you with everybody here on the call. Can show you like here's a peek inside the machine. That's basically a camera looking in. And you can kind of see the preheat cycle there. So what we'll do is record basically a version of this where the part's actually printing. So you can see that, and you'll see the profiles that we looked at earlier today. That way you'll get a good example of what it looks like when it's working.
Excellent. Well, to that end, we're right at 3 o'clock, so I want to wrap this up. I do want to thank everybody for being here, and I want to especially thank Alex and the team at 3D Chimera for a great presentation. Thanks for answering all of our questions, Alex. I think it was great. If you have any more questions, you can email us directly. I'll put the information in the chat, but you can email us at info@beckatt.com, and we'll be happy to answer any questions. I'll also put a link for our website, the Sintratec page on our website, where you'll be able to find all more information. And Beckatt is an authorized reseller for Sintratec, so we're happy to help you if you have any questions, provide any resources, brochures. Anything else before we get out of here today, Alex?
Well, I'm all good. I'll stick around for a few minutes. If anybody has any questions that you'd like to stay on the line, I'll be happy to address those. But I just appreciate everybody for your time. We hope that it was informative, and certainly don't hesitate to ask more questions as we go here. We'd like to see you guys get some systems and start printing some parts.
Excellent. Thanks again, Alex. That's the end of our official webcast for today. Again, thank you everybody for coming and participating. If you have any more questions, let us know. And thanks, Alex, for sticking around. I'll also stick around for a few minutes in case anybody wants to continue the conversation.
Okay, cool.
Is that, Alex, is that a nylon part or a TPE part?
Yeah, this is a nylon part. This is actually part of a part a customer uses these to build parts of RC cars. This is like the shock system on the RC car. I'll just show some examples of parts here. So this is kind of a cool piece here. This is for a university, so I can get a good angle on that. Inside of that is kind of like there's a double helix inside of there somewhere, which is pretty neat. Let's see. This is a part here that's printed with the glass bead material, so it's hard to tell the difference, but basically it's way harder, like in your hand. You can feel it. It actually has almost like a kind of a colder surface to it. Yeah, you could do little figurines. This is kind of a neat part. Interlocking features there.
That's a very cool part.
Yeah.
Is the glass bead material out, Alex, available right now?
It's not available to the general public yet.
Okay.
So here's kind of the TPE. Very, very flexible.
What are you finding more customers are liking more, the nylon or the TPE?
I would say the vast majority of customers are working with the nylon, the PA12. I think it's what people understand the most, and it's just really incredible. Like, I mean, the strengths are ridiculous. You know, we've had we had a customer on that strength part. This was the part, right? Yeah, we had one customer who printed this part as like this is one of the first parts we asked people to print, and like he bought a system, and they actually ended up hooking this thing up onto like a forklift and hanging like I don't know, like an axle from like a 1980s Jeep off of it, and then had like three of his guys standing on it, and like this part still held, which is like mind blowing. So the strength of the nylon 12 parts I think it's really like a game changer for people. A lot of people are familiar with like what ABS can do or what PLA can do. I mean, this is like an order of magnitude better in terms of performance. So, we have people who are doing all sorts of functional parts from like under hood components to, geez, I don't even know, engineering lab equipment, engineering test fixtures. We have a lot of people who use it for end use parts. So they're actually producing parts for production. They're sold on the market. So it's a pretty big, it's like a giant leap in technology for most folks from FDM to SLS, and being able to do that in-house affordably is a pretty big difference.
Sure seems like it. What's the durometer of the TPE?
Yeah, do you know what the durometer is on that TPE? We measured that one time, right? It was like a 40A, I think.
It's like, depending on your brand, it's between 45 and 60.
Yeah, so durometer is one of those tricky characteristics to measure mechanically. So yeah, we're looking at somewhere between like 40 to 60 short A durometer on that TPE, which is actually pretty soft, like super soft, way softer than you can do in the FDM process because we don't have to push it through anything, right? So we can just start with a soft powder and sinter it. Yeah, it's a
To that end, Greg replies with really with 3 exclamation points and 3 question marks, and then come on with 4 exclamation points.
I know, right? I mean, look at that, dude. It's soft. It's some soft stuff.
Yeah. A couple people have asked about. I'm sorry. Go ahead.
I was like, Gregory, you gotta get a part here from the team so you can check it out yourself. We've got a durometer tool we measured off of from McMaster. Maybe you have some like better equipment. We'd love to see what your results are.
Okay. Alex, a couple of people have asked about the price of the systems. Can you just,
Yeah.
I mean, so for anybody who's on the call, feel free to reach out to me directly. Everybody has my contact information, but if you could just quickly touch on the overhead price.
Yeah, absolutely. So the S2, the base price is like just under 40,000. I think it's like 39.9. And that basically gets you the, kind of the setup that we see here. So that's going to be the cleanup station, the cart, and the sintering station. Now, with that, you need to get like a material startup kit, which is going to get you, the vacuum system here and the drums that you need in order to operate the machine. So we usually see, right around the 40K mark is like the bare minimum price. If you are really looking for maximum efficiency on the machine, we always recommend a second material handling cart. What that allows you to do is as soon as one part is finished with printing, you're able to remove that cart, allow it to cool in the cleanup station, and you can put another cart right in and immediately start doing a second print. That adds about $10,000 to the system. And then, of course, our training and support plans, and lots of people load up on materials up front. So you're certainly looking at a serious investment, but I don't think we've ever seen an order come in, over 100K, and much are significantly lower than that, in the 50, 60K range. So it varies depending on the package you want to put together.
Well, and then the kit is very affordable, right?
Yeah, the kit is crazy affordable. The kit is basically is the least expensive SLS 3D printer available on the market. It is available literally as a kit that you put together. It's like a little over 3,000 pieces. It takes about literally 40 hours of work to put together. So it's a significant undertaking, but it's definitely doable for any technical person. You don't have to be an engineer or anything like that. An intern or something could do that. The kit itself is a great way to learn the SLS technology. It's the only kit available on the market. It's the initial product that Sintratec entered the market with, and where they gained all their notoriety and fame from. It's still pretty much unchanged from the original version of the kit. And as you've seen, I mean, the performance you can get out of it is really incredible when you work into getting it all fine-tuned. And that guy is right around $6,000 for the basic kit. And if you're interested, of course, we can offer that assembled for an additional fee. So you can get started certainly under 10K. And if you're going to build it yourself, you're looking at like the 6K range.
Yeah, very affordable. What in terms of the materials, are vendors adapting to making the powders? Are these proprietary materials? Will this be as diverse as FDM materials? I mean, I could say right now it's certainly not. We're not there yet, but what's the roadmap look like?
Yeah, so that's a little bit out of our control. I think that absolutely we're going to see more powders available on the open market here shortly. The vast majority of the powders at the moment for any type of SLS 3D printer are proprietary. What we're seeing out of like a lot of the national labs and universities are folks who are actually doing materials research to develop proprietary blends of powders. And the Sintratec kit is perfect for that. So if you're looking for, if you're in the research space developing powders or like developing a new business, Sintratec kit's a fantastic way to go. The S2, we're looking at maybe like Q4 this year, perhaps beginning of the next year. We're going to have a package that you can purchase to unlock all the parameters on the S2 as well. So if you're looking to do something completely proprietary, maybe you guys make your own blended powder and you don't want any of your competitors to be able to do that. You can do that on the Sintratec S2 here towards the end of this year. So I do expect to see that ecosystem to change. I would say it's hard to say when, but like I think the more that people see SLS technology, the more they tend to forget about what the FDM process can do, because it's just such a game changer.
Yeah, Steve wants to know, what are the particle sizes in the powders? Are they in the hazardous or nano range?
Yeah, so the nominal size of the powder particle is like 60 microns. So like any particle, it's like a statistical curve, but yeah, 60 microns is kind of the nominal size. So not in the nano range.
So no full suit PPE required when handling the powders.
No full suit or anything like that. Yeah. If you were like doing something with a lot of powder, I mean, I don't know what you would be doing. Like the system does have a ventilation system in it. That's actually what you can see in the back there. That's like a kind of like a HEPA style filtration system that creates like a negative pressure when you're working with the powder. So that's going to kind of capture the vast majority of any kind of loose powder if you're working in the system. But just as a precaution, we like to wear a mask anyway. So, you know, today we get masks everywhere. So we probably just go into your glove box of your car. You probably have some in there. You're good to go. But yeah, I mean, you know, respirator or something is fine. Breaking Bad mask, you know, carpenter's dust mask is we're not worried about, you know, keeping viruses out or anything. So our normal masks that we've got out there are good to go for this.
Well, that answers Greg's question. What if you sneeze? Wear a mask.
Yeah.
It won't be a problem.
Yeah. Problem
I mean,
solved.
we've been to your office in Miami, and you've got the printers right out there in the showroom, and it's not really that messy.
Yeah, I'll show you. I mean, this is our front door, so I'll flip the lights on. We had some of the lights off. So like, this is what you would see if you walked in our office, right there where I was sitting over there with our light. Here's the S2 right there, and here are the Sintratec kits over there. This is our floor. It looks pretty normal. So it's a pretty good setup. Oh, look, we've got the system is sintering now.
Okay.
So basically, it prints a layer. It'll come across at the wiper, and then it's going to basically go through a little preheat, and then it sinters again. It just keeps going. So for those of you guys who hung out on the call, you get the extra benefit of seeing that live. That's pretty cool.
Yeah. I could sit here for an hour and watch this thing.
I know, it's kind of nuts. What's weird about
mesmerizing.
This, it is. What's kind of tricky about this one is it's like harder to show people when it's not live because you can't capture like a time lapse as well because it's like really exciting for a couple seconds and then it's like nothing. So if your time lapse is on the wrong cycle, it just doesn't work.
Oh, yeah.
So it's kind of yeah, that's how it works though. That's the process. Yeah, I'd say, you know, normal office environment, it's totally safe for a normal office environment. A lot of customers do put it in like an industrial environment. So the system is built with mechanisms to allow you to like bolt it to the wall and bolt it down to the ground. So, you know, if a forklift hits it or something, you don't lose your machine. But, you know, we just have it sitting on our floor here in the office. The key is climate control. So you do need to have consistent environmental temperature and humidity. And so as long as you've got those two characteristics, you're good to go.
Yeah, I mean that's a lot of 3D printing technologies in general. It's just making sure you have the right climate and making sure that it's consistent, right?
Exactly. That's what it is.
Okay.
It's all about consistency.
Well,
Cool.
on that note, I think we'll wrap it up. Again, I put our contact information in the chat. Of course, everybody here has my contact information directly. Feel free to reach out if you have any questions or if we can do anything else for you. Alex, thanks again. Thank you to your team. We really appreciate it. We'll do this again in the future. So thanks everybody for coming and have a good afternoon.
All right. Thanks, guys. Bye.
Take care. All right.